Okay, in the day 2 section of this video, I'm going to provide some examples for using the basic rules of differentiation, which include the power rule and the product rule and the quotient rule. Okay, also keep in mind that the derivative of any constant is 0. Let's begin. Okay, my first example is to do this problem. One of the rules we had from yesterday allows us to write this as separate problems. So we can write this as d dx of root x, and then minus d dx of 2 over x, and then plus d dx of x squared minus d dx of 1. We know that the derivative of a constant is 0, so let's just take care of that now. So this goes to 0. Okay, then let's go through here and let's write this as x to the half, and we'll write 2 over x as 2 times x to the minus 1. And as you know, the derivative of x squared is simply 2x by the power rule. We bring the power down to the front and then take away 1 power. So this just becomes 2x to the first. Okay, we can apply the same rule now to the other two terms because we've written them in a way that's similar to x squared. So like this first one, it's not x squared, but it's x to the half. So bring the half down, and then it'll become x to the half minus 1. What's half minus 1? That'd be negative half. Okay, then we have a negative here. All right, this is a minus. But we have basically, if you bring this down, a negative 2 multiplied against the 2 here. And then x to the take away 1 from negative 1. Negative 1 minus 1 is negative 2. So what ends up happening is this becomes a plus right here. And then it's 2x to the minus 2. Okay, so I tried to go through that slowly, but what I did is I brought this negative 1 down, and it became a negative 2. X to the minus 2, because you take away a power. And then there's a minus out in the very front. So, okay, and this is the end. Notice I didn't differentiate the 2x. The 2x, remember, was from doing the derivative right here. I already did the derivative for that term, so I'm not going to do it again. Just copy and paste it into here. Okay, there's your first example. Okay, for my second example, I'll do a product rule. And we know that this can be solved using the product rule because we see there are two functions here, u of x and v of x. Or we could think of this as just one function and FOIL it all together. We're actually going to do it both ways. Okay, so first use product rule. So if you want to use the product rule, you have to understand that the product rule requires us to call one of these u and the other v. So I'll just do them in that order, u and v. And since they're multiplied, the rule works like this. The derivative of uv is u times dv dx plus v times du dx. Or you may have seen it written this way before. The derivative of uv is uv prime plus vu prime. Now there's a little bit of forgiveness on the order here because we're adding. So you could do instead u prime v plus v prime u. It wouldn't make any difference for this rule. Okay, so first thing we're going to have to understand is that this becomes basically a 4-part answer. And I like to think of it as fill in the blank. So right here, I'm going to be putting my u. This will be v prime. That's just the derivative. And this is v, and this is u prime. And this, remember, is u and v. So we got half of this for free. This is just x squared plus 2x. And this is just x cubed minus 3. Okay, next to our u, we have v prime. So the derivative v prime, or you can call it dv dx, is 3x squared minus 0 because the constant here gives us derivative 0. Okay, so this is just 3x squared for the v prime. So that goes here. And then next to our v, we have u prime. So u prime is 2x, that's the derivative of x squared, plus 2, that's the derivative of 2x. Okay, so this becomes 2x plus 2 right here. And you're welcome to just leave your answer like this or FOIL it all together. Okay, the second way is to use FOIL first. So basically expand and then do the derivative. Okay, so what happens if we expand this original problem? We're going to get x to the fifth minus 3x squared plus 2x to the fourth minus 6x. Okay, now we don't need the product rule for this. This becomes more like my previous example, see? So we just do this in parts. First we do the x to the fifth, so that's 5x to the fourth. Next we do the 3x squared, which is going to bringing the 2 down, it's going to become basically 6x to the first. This next term is going to be 8x to the third, and the derivative of negative 6x is negative 6. There's a couple ways to think about that last one, in case you didn't catch that. Why is the derivative of negative 6x negative 6? It's because negative 6x is a line with a constant slope of negative 6. So the derivative is simply negative 6. The other way of thinking about it is to think of it as negative 6x to the first, and when you drop this down you get negative 6 times 1, x to the 1 minus 1, so you take away 1. So what you're left with is negative 6x to the 0, in other words negative 6. Okay? Alright, now let's move on and do another example. Okay, our next example is a quotient rule example. You can tell from the way this problem is written that it actually is a quotient. So you have one function on top, which we can call u of x, and one function on top, u of x, and one function on the bottom, v of x. Okay, so the quotient rule is a little bit hard to memorize, but it looks like this. It's low d high minus high d low all over low squared. So this is, again, just a little mnemonic. It'll help you memorize the quotient rule. Okay, so we're going to use the quotient rule. Alright, now in our last example we did the problem 2 different ways. There is a second way to do this problem using product rule and chain rule, but we aren't learning the chain rule yet. So let's just go ahead and do the quotient rule only. Okay, so the quotient rule is low d high minus high d low all over low squared. Or if you want to write it symbolically, it's d dx of u over v is v times du dx minus u times dv dx all over v squared. Or maybe you've seen it written as u over v's derivative is basically u prime v minus v prime u over v squared. It's the same thing. The first one is Leibniz notation. The second one is Lagrange notation. Okay, let's try it out. So again, it's a 4-part thing on top, this time with a minus. And then on the bottom we have this. Okay, so we basically need first u prime. So u prime, we can calculate up here, it's just 2x, because the derivative of x squared is 2x and the derivative of 2 is 0. Okay, so that's going to go here, 2x. And this blank is supposed to be v, so you have rad x minus 1. And I'm going to start writing using power notation, so exponential notation, or I should say rational exponents notation. Okay, so there's u prime v minus, and then I need basically v prime u. So v prime, we need to work out. Remember, this is just x to the half minus 1. So the derivative v prime is 1/2 x to the half minus 1, in other words negative half, minus 1. Remember, the constant here is going to have derivative 0. Okay, so this is just 1/2 x to the minus half. And then this space is reserved for u itself, so that's just x squared plus 2. And the denominator is basically the original denominator with a square on it. And there's your answer. Okay, we'll just circle that. Okay, this next example, the easiest way to do it probably would be to FOIL the top and the bottom, and then to apply the quotient rule once. But there is another way to do it. Okay, so I'm going to actually treat the top function as u and the bottom function as v. And before I even do this problem, I'm going to write down u and v right here. So I have x minus 1 and x squared plus x. And for v, I have x plus 3 and x squared plus 1. Okay, so I'm just recording those because this is going to get pretty messy. Okay, now I'm going to go on and find basically u prime. U prime is going to be a 4-part ordeal because we're dealing with a product. Okay, so this is now like f and g, see? So to get the derivative of u, I need to apply the product rule. So first I start by taking g times f prime. Well, f prime is just 1. F prime would be 1. The derivative of x minus 1 is simply 1. And then g prime would actually be 2x plus 1. Okay, so this would be basically gf prime plus, and then here I have fg prime, see? So f would go here, and g prime would be 2x plus 1, that goes here. That's g prime. So that's very messy, but that's what we have. Okay, I'm also going to find v prime while I'm at it. V prime is going to be, if this is like our f and g now, f prime would be 1 and g prime would be 2x. We're going to piece this together for v prime now. So v prime would be gf prime, so that'd be x squared plus 1 times 1, plus, and then it's fg prime, so x plus 3 and 2x. Okay, so now we can simplify these if we want to, probably a good idea. This gives us x squared plus x plus 2x squared plus x minus 2x minus 1. So the first one's just x squared plus x, and then the next one's a FOIL there. Okay, in grouping like terms, we get 3x squared plus 2x minus 2x, so there's no x's, and then minus 1. So in other words, this and this made 2x, and cancel with that. Okay, so it's 3x squared minus 1. And v prime can be simplified to be x squared plus 1 plus 2x squared plus 6x. In other words, 3x squared plus 6x plus 1. Okay, so hang on to these. It's time to construct our quotient. All right. So the quotient would be, I'm switching rules now, so let's just go straight to the quotient rule in green. So the quotient rule is supposed to be vu prime minus u prime v all over v squared. Okay, and I need the original u and v, which are up here. So this was u, remember, and this was v, and then this is u prime, and this is v prime. So I need those 4 objects. So I have v u prime, so this is v, and here's u prime, minus u prime, I'm sorry, I wrote my rule wrong. I put my prime on the wrong one. I already used u prime, right? So there's 1 of each. I should have written vu prime minus uv prime. Okay, so this is my v. So there's no math errors here. I just did a little copy error there. I copied u prime twice there. So we have v there. This is u prime minus, and now I need u and v prime. So x minus 1, x squared plus x, there's u, and v prime, that's right here, 3x squared plus 6x plus 1. All of this is over v squared, which is x plus 3 times x squared plus 1 squared. Now you might say, Mr. Shore, you could easily have FOILed this out in the first place, and then it would have been much simpler and simplified. Okay? You're absolutely right, but there comes a time when we can't do that. And we need to understand that these rules can be used one after the other like this. So I did a product rule and a quotient rule. This problem could have been easily done by just foiling it and doing the quotient rule exactly once. But I would not have been able to show my point on this. Okay, for our next example, you see that we have a function with a power on it. So this can be a little intimidating. We're going to talk more about this later. If you have a composition of functions, how to handle that. But there's a rule called the chain rule that we need to know. All right, so what we're going to do on this one is we're going to first try to deal with this minus 1 algebraically. And then I think we'll be in a situation where we don't need any new rules at all. So this, remember, means just to flip the fraction over. And I'm going to go and write that rad x as x to the half. Okay, so when you look at it now, it's just a simple quotient rule problem. But also watch out for this situation, because we don't have to use quotient rule here. We can split this up into two fractions. So this would give us d dx of, now 2x squared over x is simply 2x, right? And for our second fraction, we have 3x to the half over x. That's like having 3x to the half over x to the first. So you can just do basically 3x to the half minus 1. So this is just going to give you 3x to the minus half. Now we haven't done any calculus yet. We've just got this problem set up where it's a little bit easier to understand. And now the derivative is simply 2. That's for the 2x. Right? And then minus, be careful here, you're going to bring this down. Right? So it's going to be a negative 3 halves. X to the, and then you're going to be taking away 1 from your power, right? So negative half minus 1 is negative 3 halves. And there's your answer. You can leave this as exponential form like that if you like, as long as the back of the book agrees. Otherwise, you're going to have to switch it to this. And then you can just write it as 2 minus 3 over 2x to the 3 halves. I just want to remind you of a small subtlety. If you decide to go all the way to radical form, you're going to have this. Okay? Because there comes a time where you're trying to break this down. And this is x squared times x. And the square root of x squared is absolute value x. So you just have to be careful about that little absolute value there. That will show up later in the end of chapter 3, again, that absolute value. But this would be a good answer too. The only time you don't need the absolute value x is if the problem states explicitly that x is greater than 0, then you wouldn't even need it. Okay, our next problem is to find the horizontal tangents of a function type problem. So you have to remember that there are certain points on graphs, namely relative minima and maxima, where if the graph does have a derivative and a tangent line can be drawn, that slope might actually be 0. So these are really important points on a graph. They represent the least of something or the greatest of something respectively. Okay, so these would be points where at the point a comma f of a, we have f prime of a being 0. So the derivative is 0 at that point. And the same is true for the one over here, the relative max. Okay, now not every relative minimum and relative maximum has a slope of 0. Sometimes we know that a point like this one, these are corners or maybe a cusp, those points we can't even draw a tangent line. So actually a relative minimum or relative maximum can occur at a point where the derivative is 0, namely this horizontal tangent line, or it can happen when the derivative is undefined. Okay, so that's important to keep in mind. This particular problem is about a polynomial. Okay, and it is real numbers domain. It is fully continuous. It is fully differentiable for all values of x. So we're dealing with points more like these up here. Okay, now you also learned that since this is a degree 3, there can be at most 2 turning points, which means we might have a relative minimum and a relative maximum at most. So one of each. Okay, so let's go ahead and take a moment, and instead of graphing this, let's just take the derivative and set it equal to 0 to see if we can find those points. Okay, so let's find y prime. This is our strategy. We're going to find y prime. We're going to set y prime equal to 0. Okay, so find the derivative, set equal to 0. Write that a little nicer. Solve for x. And then we'll see what we can do with the equation of lines. Okay, so the derivative is simply 3x squared plus 2x minus 2. And if you set this equal to 0, you're going to get the following two values using the quadratic formula. So x is going, remember you do x equals negative b plus or minus square root of b squared minus 4ac, so that's 4 minus, and then basically 4 times negative 6, so negative 24, all over 6. So that's 2a. Okay, so we end up with an exact answer pair of negative 1 plus or minus rad 7 over 3. Or if you're going to go with decimal equivalents, let me punch that in real quick. All right, just typing this in. We're talking about 0.5486 and our other root, negative 1.2153. Okay, so these are two x values where we would expect the graph to have a relative minimum or maximum. Now we know that a cubic, especially one with a positive leading coefficient, would have end behavior that looks like this. So I'm suspecting that the x equals negative 1.2, that is our relative minimum. I'm sorry, our relative maximum. So like that. And then the other one, which is x equals, this should be at, negative 1.2 on the x, so maybe just past negative 1. So this is the point there. That's your x for the relative maximum. And then at 0.5, so right in here somewhere, we have our relative minimum. Okay, now, these are the two x's, but they asked for the horizontal tangents, so they want these two lines. And what's going to happen is we're going to go ahead and find those two lines, and we're going to realize that my graph really isn't that exact. Okay? But that's okay. I'm just trying to get the hang of it right now, trying to get the feel for this problem. Okay, so having these two x's means I can find the y coordinates of these 2 points here. Let me make them green so you can see them. I'm talking about this point. At this point, I have the x's, I want the y's. Okay, so the easiest way to do this on the calculator is to go ahead and enter the function they gave us as y1. So just entering the x cubed plus x squared minus 2x. And then going to the home screen, we could type y1 of 0.5486 and y1 of negative 1.2153. And the calculator will give us the y values very, very accurately. Okay, so y1 of 0.5486 gives me negative 0.6311. And we're losing accuracy as we rounded multiple times. So I'm just going to leave it as negative 0.631. And then we're going to rerun that, this time with the other root of the derivative, 1.2153. So this gives me 2.113 if I round it to the nearest thousandth. Okay, so I'm just going to take a look at the graph now. Obviously my graph isn't that great. You can see that I have the point on my graph for negative 1.2153. My y coordinate is certainly not 2.113. You can see that I should have had the point up here, see? So the graph is more like that, see? And then we also know that this graph passes through the origin, right? I mean, look at the original function. Plug in 0, you get y equals 0, right? And the other value that was wrong that I had here was, if you look at this point, I had it basically at 0.5486, and for y I should have been getting negative 0.631, see? But obviously mine's further down than it should be, maybe. So that point maybe should have been a little higher up, maybe here. So that's what I should have had. I'm sorry. I should have had negative 0.63, and I have it too far down. So this is maybe more what the graph looks like, if that makes sense. And we can validate that on the calculator. So let's do that real quick. So you could turn on your calculator, right? Enter in the function and simply graph it. Zoom in maybe if you like. Oops. Let's fix the window by hand. Something funky about my zoom there. Let's just do -5 and +5, and the same thing for the y's. Okay, so here comes the graph. It is more like my upper graph than my lower graph. And then you can also use like CALC trace to get the maximum point over here. I don't mean CALC trace, I meant CALC maximum is what I chose there. You can run through this little wizard to get that point. Negative 1.2153, comma 2.113. That's very accurate. That's what I have as well. Okay. And what we're saying is that the equation of this line is y equals 2.113. There's one horizontal tangent. And now let's go ahead and do the other one. So now we're going to go into second calc and do the minimum over here. So I want to find this minimum point, like that, and it's 0.5486 like I had, comma negative 0.631 like I had. So this is the equation y equals negative 0.631 for that line. So it's just kind of nice to see that those really were the relative max and relative min respectively.